So, good afternoon, good morning, or good evening, everybody, depending on your time zone. I'm very happy to see that today we have a lot of people that are joining us for this new webinar of the Commission on Volcanogenic Sediments. Today we have the pleasure to have Dr. Federico Di Traglia from the INGV of Italy. He will talk about hot volcaniclastic sediments as a source of pyroclastic density currents, observational and modeling constraints. As always, you can tape your question during the presentation, and at the end I will read all the questions to Federico, and Federico will answer to your questions. Please, Federico. Thank you.
Thank you, Andrea, and thank you to everybody. Good afternoon, and thank you for being here for this presentation, for this webinar. So, what I'm going to show you, and the topic of this presentation are the so-called deposit-derived pyroclastic density current that are avalanches of hot volcaniclastic material that can be originated by the instability of high temperature volcaniclastic deposits, by the failure of the crater rim, the failure of deposit emplaced during the explosive eruptions, or the crumbling of lava flow fronts. One of the mantra in the studying of deposit-derived PDCs that these kind of deposits are, these kind of events are uncommon. Our experience is that they are very common in few volcanoes. So there are specific context, specific feature of some volcanoes that can help the material to fail very frequently, and there are some other features that cannot be useful for the generation of deposit-derived PDCs. So we identify these events in different geographical contexts and geological contexts. They are mainly associated with mafic magmas, but not only mafic magmas can generate deposit-derived PDCs, but they are always associated with steep-sided volcanoes. They are small volume PDCs with run-out distances up to several tens of kilometers and a wide range of flow temperature. In the scientific literature, we recognize a lot of different names for the same phenomena. The oldest description of this phenomena derives obviously from the Vesuvius in the 1822 eruption. In the book that described the eruption by Monticelli and Covelli, they describe the deposits associated with multiple crater rim failure at the Vesuvius as lava a rottami incoerenti, so a lava flow made by debris. They describe the pieces of larger class together with a sandy matrix. Then we have three different names for the same events: the Stromboli 1930, hot avalanches by Rittmann, avalanches of pyroclastic material by Abruzzese, and pseudoflows by Imbaud. Imbaud, that was the former director of the Vesuvius observatories, used the same name also for the deposit-derived PDCs occurred during the 1944 eruption in the Vesuvius. Then there are more recent names like glowing avalanches for the Fuego 1974, pyroclastic avalanches for the Neuroi 1975, and the deposit-derived PDC by Risica and co-authors for the Stromboli 2018 event. So we choose to use the last name, deposit-derived PDCs. Here you can see the distribution of these events all around the world. I included also the Piton de la Fournaise related to the last eruption. The fracture that this is feeding the lava flows in the Piton de la Fournaise generated the collapse of an older cone, and this collapse, so the mixture of older material together with new lava flows generated a deposit-derived PDC. The first example of observation and modeling of this kind of events in the modern volcanological description derives from for the Volcano Arenal. There are two very important papers, the Alvarado and Soto 2002 and Cole and co-authors in the 2005. They describe the eruptive activity, some monitoring parameters, and the deposits. So there are very important works on these events. And the Arenal can be used as a case studies for the Arenal type PDCs. So the failure of the material generated by magmatic forcing. So the magma thrust in the conduit and generated the failure of the crater rim. And we can recognize different Arenal type PDCs at Arenal, at Etna, Piton de la Fournaise in Stromboli, and Vesuvius. The other kind of PDCs can be associated with the 2018 Volcán de Fuego event, with a failure of the material deposit on the in this large scar very close to the summit of the volcano. So where then during the failure, with the different pulses were generated, the different pulses of PDCs by the collapse of the material within this large scar. So the Fuego type PDCs is mainly associated to the accumulation of material and slope overloading, and this combination generated a variation of the slope and the overloading of the slope by new deposits or lava flows and other mechanisms, like for example the undercutting on the slope. And we can recognize these events in Fuego, Fuji, Naroi, Stromboli, Tungurahua, Vesuvius. So in this presentation, I will show you data from Vesuvius and Stromboli. We have a lot of data about these two volcanoes, but also some modeling approach in the for the Arenal and Fuego. So I will start to show the eruptive activity associated with this kind of events. So we'll start with Vesuvius in 1944. The Vesuvius recent activity after the 1631 subplinian event was mainly a semi-persistent activity with a lot of lava flows, strombolian activity, and sometimes some so-called Vesuvian paroxysm that were violent strombolian to subplinian events. One of these events was the 1944. There were the changing the eruptive style from effusive to violent strombolian to subplinian, Vulcanian, and final ash emission during the last eruption of the Vesuvius. And the deposit-derived PDCs occurred during the violent strombolian phase. So the violent strombolian phase generated a large accumulation of coarse-grained material very close to the vent, and this material used to fail soon after the emplacement. So the chronicles of the eruption by Imbaugh, that was the director of the Vesuvius observatories, he described 8 lava fountains with the deposition of coarser material on the cone and on the lava platform that filled the crater of the Vesuvius before the eruption. On the left photograph, you can see the detachment scar and the different flows of deposit-derived PDCs that were generated by the failure of the material deposited by the Valium Strombolian phase, and on the right you can see the generation of PDC by column collapse during the subplinian and the Vulcanian phase. As I told you before, the Vesuvius was completely different, with a large lava platform on the crater area and the summit area, and some lava flows all around the cone. All these lava platform and different flows were generated after the 1906 subplinian event that completely destroyed the northern part of the cone. So here you can see the detail of this lava platform and the steep slope of the cone before the eruption. This is the slope map, and on the right you can see the sky vector map. And this is the present day morphology of the Vesuvius, with the large crater on the cone, the detachment skull all around the cone, and some of these scars were generated where the lava platform was present. So we need an accumulation of the material reaching a critical angle to generate a collapse. And here you can see the distribution of the different lobes of the PDCs associated with the failure of this material on the post orthophotomosaic and digital elevation model. The dam of difference, the dam of difference for the events allowed us to constrain also the volumes of the different flows and the mobility parameters. So the largest event was on the eastern side of the Vesuvius, with more than 3 millions of cubic meters of materials that failed. And the larger flows are on the north, on the east, and on the southern side, while on the western side there are smaller deposits. Moving from Vesuvius to Stromboli, just to constrain eruptive activity that can be associated with deposit-derived PDCs, in Stromboli we detected a lot of them. So Stromboli was one of the main generators of deposit-derived PDCs in the world. They can be generated by the failure of the crater rim during the onset of lava overflows from the crater terrace, the failure of the volcaniclastic deposit on the slope generated by both the opening of ephemeral vents during flank eruption, or the mixing of the crumbling of the lava flow with the volcaniclastic deposits. One example of this is the 2014 eruption, with a lot of PDCs generated by the failure of material during the run-up phase of the eruption from late May 2014. There were a lot of failure during July 2014, and the major collapses occurred at the onset of the effusive phase between the 6th and the 7th August 2014. Isolated events were detected, for example, in 2021, and we detected the failure of the crater rim, but also the generation of PDCs by mixing of the crumbling of the lava flow and the volcanoplastic deposits present on the Charade photoslope. It was the same in October, December 2022. We detected a lot of them, 2 main crater rim failure, and then a lot of slope failure generated by the mixing of lava flows and volcanoplastic deposits. It was the same into 2024 with the complete collapse of the northern sector of the crater terrace and the generation of a big canyon on the Chalet del Fuoco with very frequent multiple events of both cratering failure and failure of deposits. It was incredible, the number of PDCs that were generated in 3 days. Here you can see the opening of this phase with a lot of also co-PDC ash plume. This was the increasing in the ash plume during the failure of the crater terrace, but the failure of the material continued for 2 days, and here you can see the deposits of the previous days during the generation of new PDCs and ash plume on the 5th of July. And these 3 days generated ash deposits all around the island with a very thin layer in distal location and accumulation of accretion and rapilli in proximal locations. So moving from the eruptive activity to the monitoring of the instability, we have the availability of the data of 2 ground-based INSAR instruments installed in Stromboli. They were able to detect ground deformation and before the slope instability, and they are very important because we can combine the ground deformation with other geophysical parameters, like, for example, seismic tremor and VLP and so on. So this is, for example, for the 2014 eruption in Stromboli. Here you can see the occurrence of PDCs generated by the crumbling of the lava flow fronts during the run-up phase of the eruption and the major events associated with the failure of the northeastern part of the crater terrace at the onset of the eruption. You can see the increase in the ground deformation and in increase in volcanic tremor. The volcanic tremor is a proxy for the increase in the magma level within the conduit. So we can say that the increase in ground deformation was associated by the increase in the magma level. It was exactly the same for the October-December 2022 activity, with increase in displacement rate weeks, 2 days before the lava overflows, and a strong increase soon after the events. It was the same for the 2024, so there was a strong correlation between the instability and the increase in the eruptive activity, and the increase in the eruptive activity and the ground deformation anticipated the failure. So there was a strong correlation between the increase in the activity and the failure. So we can move one step back to the Vesuvius to study the proximal deposits, because we would like to understand what kind of deposits can fail during this kind of PDC generation events. So the proximal deposits are very complex. They are mainly spatter and lapilli ash with different degree of welding. So we use an approach proposed by Kay and Kotos in the 2008 to study the welding degree, studying both the matrix and the cluster, the larger cluster of the proximal deposits in different locations all around the crater rim of the Vesuvius. Study, for example, the flattening of the deposit, the kind of matrix, how the matrix is sintered or not. This is just an example of one section with a different feature for each section. We also recognize some structural feature, for example, slip plane within the deposits. This is an example. So we recognize different welding degrees, but also the presence of a sliding surface within the proximal deposit. These failure surfaces are all around the crater rim, and we recognize that the more weathered patches are preserved along the crater rim, outlining the margins of detachment scars, while the less units failed and were incorporated during into the PDCs. We use also a geomechanical approach to study the proximal deposits, trying to understand the resistance of the material, because we would like to move from the observation to the modeling, in particular the slope stability modeling. We use a 2D slope stability approach combining two different failure mechanisms, the Oken-Brown and the Barton-Chiarnali failure mechanism. And we choose this approach because in this way we can use both the resistance of the material and the presence of discontinuity, mainly stratification within the slope. And we started from Stromboli because we can make back analysis of the failure events, combining the slope stability modeling, the topographic data used by, for example, drone topographic surveys, but also the ground deformation. And it was amazing to see that there was a strong correlation between the factor of safety, so the results of the slope stability modeling, with the ground deformation associated with the failure in the 9th of October 2022 at the 4th of December. So the more unstable phase without magma forcing were exactly the area affected by more ground displacement rate before the failure. We apply the same for the slope of the Sharp Fogo, trying to understand if the failure of the volcaniclastic in field can be detected using a ground a slope stability modeling. And we recognize the area affected by thin skin and diffuse instability also in this case. So we move from Stromboli to the two main case studies, Volcán de Fuego and Arenal. In this case, we so combine the different approaches generating a slope stability modeling, but we would like also to include different scenario based on rock strength, because in this case, we don't have a field survey, so we use different combination of resistance and the different combination of stratification of the materials. And in particular, we use this combination of rock units with different geomechanical parameters and this different scenario of stratification, so no stratification or densely stratified material. And here you can see the two examples. On the left side, you can see the Fuego results without the presence of discontinuity, and on the right side, the results on the Fuego stability slope stability modeling using the stratification within volcaniclastic deposits. And here you can see the surface with minimum factor of safety, but the diffuse instability in the scar of the 2018 events. So without the certification, we cannot identify the actual area of instability at Fuego. But it was exactly the same for the Arenal. With no discontinuity, the scenario is completely different with respect the ones including the discontinuity that is able to identify the area where the crater ring failure occurred during the 90s. So this is just a summary of the effect of the different combination of different materials, different stratification, and different magma thrust. So moving from all these observation and modeling to the conclusions. The Fuego type PDCs are events where the predisposing factor are mainly the slope angles. So we need a high slope angles, and the mechanical properties of the material, but mainly the presence of discontinuity within volcaniclastic deposits. And the triggering is always the accumulation that can change the volume of the material, the loading, and the angle of the slope. And also in this case, we can have retrogressive failure. For the RNL type, we need exactly the same predisposing factors, but we need also the presence of volcanic conduit at short distance, sufficient to transmit the volcanic thrust, the magmatic thrust to the crater rim. So because the main trigger is the magmatic thrust, related to the variation in the magma column within the conduit, the densification, so the relationship between the effusive activity and the failure is clear. So we need a dense magma, and probably we need a new magma that push the dense one against the crater rim to generate the failure. And also in this case, we can have retrogressive failure. But the deposit-derived PDCs can be considered a part of a wider spectrum of gravitational induced PDCs. The other are non-failure PDCs, non-collapse PDCs. So we can have the deposit-derived PDCs that are associated with weaker, stratified, hot volcaniclastic deposits, while the non-collapse can be associated with denser, stronger, and massive lava bodies. And in between this stuff, we can have a continuous spectrum of, for example, lava lobes, plastogenic lava flows, hot ignimbrites. So in one case, we can have the failure control related by the pure gravitational forcing by accumulation of material and changing in the slope angles. And in the case of the arenal type and in the Pelean type, we can have the magmatic thrust or magmatic overpression as trigger for the failure. So here you can see two very recent papers on the modeling part on the left and on the monitoring part on the right. Thank you for your attention.
Thank you, Federico. You perfect on time. Thanks a lot. It was very, very interesting, your presentation. Let's see if someone has a question from the audience. You can write in the chat or in the D and there tool. Okay, allora proceed. Sorry. Okay, from Nemi Walding. I love the approach using geomechanical parameters to investigate the failure surface profile. Sorry, I can't turn my microphone on currently. I was wondering, how significant do you think alteration of certain layers weathering surface, for example, will be on the failure surface? For example, a clay-rich deposit having a higher angle of repose?
Okay, in the case of very fresh failure like this one, so the clay is quite not common, so you need more altered material to generate clay, but we are working on it. For example, there are a lot of dome failure, dome collapse, where you have the simultaneous collapse of altered material in the previous crater and the new material of the new dome. For example, the Boxing Day in Montserrat, the 2015 event in Colima, but there are a lot of them. And so we are moving from the very fresh material to the altered one with a very recent project. So we would like to investigate this stuff because it's very important. So before I saw the presence of Agata Pogani, she's working on this and she did a very good stuff for her PhD on the effect of alteration on the resistance of the material. So I think that that can be very important, but not so important for this kind of events where the material are very fresh and they involved quite fresh material. So I think that they're important, but not in this case.
Okay, thank you. Other question from the audience? Yeah, thank you. Let's see. So I have a little questions, maybe quite strange, as generally I work in Asian contest. Do you think that those kind of deposits could be extremely different from debris avalanche deposits?
Okay,
To
so
interpret it, I mean.
the deposit part will be another step. And
Okay.
I think that we need a lot of work on this. We have some projects, but probably we need a lot of collaboration because they are all around the world. So we need to work closely to people that work on deposits. In the Vesuvius case, we found some similarities with avalanches, with debris avalanches. For example, there are a lot of failure surface with evidence of shear, and we saw also the shift between a planar sliding and the debris avalanches. The deposit at Vesuvius for the 1944 are quite similar to avalanches. This is a mixed process. So it started like a landslide. If he had time, it became a PDCs with a lot of ash. And so the final deposits is it's a mixer, and it depends on the time of the evolution of the process. But one of the main problems for this case is that if we go in the stratigraphy, we can recognize block and ash flow or bomb and ash flow, and there are other processes that can generate this kind of events. So probably we need to work a lot on this deposit to try to understand which are the feature that can be used to recognize that one PDC deposit or one avalanche deposit was generated by the failure of hot material. Yeah, because so you can go in the field, you can recognize only. I recognize one deposit in Stromboli, and we know that was a deposit-derived PDC because in Stromboli the PDCs are outside the shadow focal are always deposit-derived PDCs, but only because we know that, not
because you
there
can
is
observe them. Okay,
yeah.
sort of. Yeah. Okay. Thank you for your time. This is Veronica Orozco Del. Would a LAR deposit behave like a normal debris avalanche would? How does the water change the modeling?
Yeah, in this case, we assume that there is no water because the material is very hot. Okay, so obviously, if we include the water, we need to include also the pore pressure and in the modeling, and we can do it. For example, for deposit-derived PDCs generation at Mount Etna, we need to include the pore pressure because at Mount Etna there are always the snow. So there is a mixture. This is increasing in the complexity of the failure, but it can be due. But we need before to understand how it works using the observation. Few days ago, there was a new paper, the publication of a new paper of Giorgio Costa and Marco Viccaro work on the reviewing the PDC activity among Etna, and they recognize a lot of them generated by also the interaction with the snow.
Okay. Thank you. We have thank you so much. Watching all the way from Colombia. Lovely talk. Thank you. This is Dave McGarvey. Thank you. How important is wind direction in controlling where material is accumulating and likely to fail and form dd-PDCs?
Okay, so the coarse material used to have a ballistic direction. So the main control is associated with the local morphology. Obviously, also the violent Strombolian jets can be quite moved by the wind, but the main control parameter is the morphology of the cone because this material used to have a ballistic trajectory.
Okay, thank you. Very interesting talk. You're receiving a lot of questions.
Thank you.
Generally, the audience is a little bit shyer. So it's very, very happy. Okay, I think we can close here now. Thank you for your time, Federico, and thanks for your very interesting presentation.
Thank you.
I would like to remind you that the presentation is recorded, so you will find this presentation on our YouTube channel. Next presentation, wait, I have the mail. Next presentation will be held by Lucia Capra-Pedol from Mexico. She will talk about erosion and aggradation on active volcanoes, 2015-2025 La Earth activity at Volcán de Colima, and it will be everything is directly, sorry. It will be on at the end of April, if I'm not wrong, was the like 22 or 28. This one, 24 of April. Okay, about the time at which the webinar will be held, we will communicate it by our social media. So follow us on our social media. And I would like just to remind you that we are still organizing a field trip. The field trip will be held in Patagonia and will be held in October, between the 19th and then 23rd of October 2026. We still have some places, so please look on our website. Okay, we have all the information there. You can apply. We have an application there, and then we will communicate how many people will be able to participate. We hope that all of you found this talk interesting. I think so. And see you next time. Thanks a lot again, Federico. Bye-bye, everybody.
Thank you. Bye-bye.